Student, I am your M.Sunderchand. Today we'll discuss about physical and the chemical properties of haloalkane. So we'll start from physical property of haloalkane. Point number 1, solubility of haloalkane in water. So here, haloalkanes are insoluble in water because they are unable to form hydrogen bond with water molecules, but they are soluble in organic solvent like ether, benzene, etc. Before explaining this thing, let me tell some general concept for the solubility of organic molecule in water. As water molecule is a polar molecule, so most of polar organic molecule, but not all, are soluble in water. This is because this polar organic molecule can interact with water molecule by the formation of intermolecular hydrogen bonding in between them. So let me give one example here. Ethanol is dissolved in water because ethanol can form intermolecular hydrogen bonding here. This is intermolecular hydrogen bonding in between water molecules. Then what about the nonpolar organic molecule? Then nonpolar organic molecules are soluble in nonpolar organic solvent, just like dissolve like principle. So for example, hydrocarbon are mostly soluble in organic solvent like ether and benzene. Now let us give the answer of this question. The question is that haloalkane are insoluble in water even though haloalkane is polar in nature. So let me give this answer. If haloalkane is to dissolve in water, energy is required to overcome the intermolecular force of attraction between haloalkane molecule and we also require energy to break down intermolecular hydrogen bonding in water molecules also. So you know how many hydrogen bond can form by water molecule. So here a water molecule can form 4 hydrogen bond with another water molecules. Here this is 1, 2, 3, 4. This is due to the presence of 2 positively charged hydrogen atom and 1 electronegatively charged oxygen atom. This means that there is a large amount of energy required to break down the hydrogen bond in between the water molecules. Now if hydrogen bond is possible to form in between haloalkane and water molecule, the energy released in the formation of hydrogen bond in between haloalkane and water molecule is less than the amount of energy required to break down the hydrogen bond in water molecule. This means that hydrogen bond that present in water molecule is stronger than the hydrogen bond that form in between haloalkane and water molecule if possible, because the amount of energy required to break down hydrogen bond in water molecule is much higher than the amount of energy that released in forming hydrogen bond in between haloalkane and water molecule. As a result, the haloalkane cannot form hydrogen bond with water molecule, and that is why haloalkane cannot dissolve in water molecule. Next point yang asiko. Next point, boiling point. Let us see the boiling point. So here point number 2, boiling point. So here we are having 2 points, A and B. The boiling point of haloalkane increases in the following order. So here we are taking the same type of alkyl group and the different types of halogen atom. Increases in the order that is from chloroalkane less than bromoalkane and iodoalkane. This is because of increase in the size and the mass of halogen atom. Due to increase in the size of mass and halogen atom, the molecular size increases from chloroalkane to iodoalkane. As a result, the magnitude of van der Waals force of attraction increases, which is responsible for higher boiling point. That means van der Waals force, let me tell about van der Waals force. Van der Waals force is a kind of intramolecular force of attraction between the molecules when the molecules are come closer to each other. And this van der Waals force depends upon the molecular size and the surface area of the molecule. If the molecular size and the surface area of the molecule increases, then the magnitude of van der Waals force also increase. This is due to increase in the electron cloud with increase in molecular size and the surface area. So in this example, the size of halogen atom increases from chlorine to iodine. As a result, the molecular size increases from chloroalkane to iodoalkane. So due to increase in molecular size, the magnitude of van der Waals force also increase. That is why the boiling point also increases from chloroalkane to iodoalkane. Let me give one example here. The order of boiling point amongst haloethane is chloroethane is less than bromoethane is less than iodoethane. So here we are taking the same type of alkyl group and different types of halogen atom. Next point, amongst isomery haloalkane. Isomery haloalkane means the haloalkane having the same molecular formula but different structure. So from the isomery haloalkane we can write 3 types of haloalkane: primary haloalkane, secondary haloalkane, and tertiary haloalkane. So among isomery haloalkane, the boiling point decreases with increase in the branching of alkyl group. The boiling point increases with increase in the branching of alkyl group because with increase in the branching in alkyl, of alkyl group, the molecule attain a spherical shape with less surface area, resulting decrease in the van der Waals force of attraction, and therefore decreases the boiling point of that haloalkane. This means that when the bulky alkyl group is present in haloalkane, then this haloalkane will attain spherical shape having smaller surface area. Due to the having smaller surface area, the electron clouds also decrease. That result decrease in the magnitude of van der Waals force of attraction, and so such molecule will have lower boiling point. So let's see one example here. Increasing order of boiling point among the isomers of haloalkane having molecular formula C4H9Cl. So by using this molecular formula, we can write the three types of haloalkane. The first one is tertiary haloalkane, secondary haloalkane, and the primary haloalkane. So amongst the isomer haloalkane, the order of boiling point increases from tertiary to primary haloalkane. So in this example, tertiary butyl chloride has less boiling point, while N-butyl chloride has highest boiling point. So in this year they have asked one question, that is, so they are giving this haloalkane having molecular formula C4H9Cl. Out of this, which isomer will have lowest boiling point for 1 marks? So for this answer, tertiary butyl will have lowest boiling point because due to the presence of bulky alkyl group, this tertiary butyl chloride will have less surface area, that result decrease in the van der Waals force of attraction. So it has lowest boiling point. So this is up to this is the boiling point. This is physical properties of haloalkane. So now let's consider about chemical properties of haloalkane. First, chemical properties of haloalkane. So we have the type of reactions: A. Nucleophilic substitution reaction, B. Elimination reaction, and reaction with metals. So we'll start from nucleophilic substitution reaction. We know that substitution reaction is a kind of reaction in which one or more atoms of the group of atoms present in a reactant is replaced by another suitable atoms or group of atoms. So depending upon the nature of attacking reagent, we have three types of substitution reaction. Nucleophilic, number one, nucleophilic substitution reaction, allotrophilic substitution reaction, and free radical substitution reaction. So here is nucleophilic substitution reaction. So let me define nucleophilic substitution reaction. It is a substitution reaction where the attacking reagent is a nucleophile, or we can give another definition: a substitution reaction in which a weaker nucleophile is replaced by a stronger nucleophile, that we call it nucleophilic substitution reaction. For your convenience, so let me explain about the attacking reagent nucleophile and which nucleophile is stronger and which nucleophile is weaker. So let me explain something about this thing. First, let us define nucleophile. Nucleophile, see here, nucleophile is an electron-rich attacking reagent which is either negatively charged or neutral molecule which can donate a pair of electrons to the substrate molecule. That means nucleophile may be a negatively charged species or a neutral molecule having one or more lone pair that can be donated to the electron deficient substrate molecule. Substrate molecule is the reactant where the attacking reagent is attacked. Have substrate molecule haibadi koigi reactant ni attacking reagent attack togudaba jagadu. As the nucleophile is negatively electron-rich species, the nucleophile is always attacked to the electron deficient substrate molecule. electron watpa substrate molecule attack tawne. So here I am giving some examples of nucleophile: OS minus, Cn minus, NH2 minus, water, ammonia. These are all neutral nucleophile. These are negatively charged species nucleophile. So the next one is that which nucleophile is stronger and which nucleophile is weaker. Karamba nucleophile is stronger no, karamba nucleophile weaker no. Haibatu khangnaba aya point shunadi piroi for your convenience. Let me keep only 2 points. Point any katang piraki yengo ko. Point number 1 de yengo. An anion is a better nucleophile than neutron molecule. Anion sika neutron molecule sika better nucleophile se anion here. Kalmarangi anion has higher electron density than the neutron molecule. So as a result, the conjugate base is a better nucleophile. Conjugate base a better nucleophile or a name. You know about the conjugate base and a conjugate acid. Kaino conjugate base habiti karino haibakanda molecule amadagi. The conjugate base is formed by removing a proton from a neutron molecule. Neutron molecule amadagi proton to oga semba that anion is called conjugate base kawe. So here water is also a nucleophile, neutron nucleophile due to the presence of lone pair of oxygen atom on of electron on oxygen. So you remove one proton from water. So when you remove proton, it will carry negative charge. So this will be a conjugate base. So this is strong nucleophile. This conjugate base is strong nucleophile than the neutral water molecule. Aduna conjugate base na neutral molecule dagi magi stronger nucleophile oini karimarangi sin electron pitopanga bi tendency nucleophilicity to wang bagini ko. In the same way here ngasi ammonia dagi when you remove one proton then it will carry negative charge purani. So this is conjugate base and this is strong nucleophile and this is weaker nucleophile. So another example is that so HCl is a strong acid. So when you remove proton here, we form chloride. When the acid is strong, the conjugate base forms will be weak. Kariyumba acid tuna strong oitaragadi magi corresponding conjugate base to weak we have. Kariyumba mu acid tuna weak oitaragadi magi conjugate base tuna mu strong oiba opposite kadab. So we know that HCl is a strong acid. So the chloride ion which must be a weak conjugate base. So it should be a weak nucleophile or an chloride say weak nucleophile or an. So here as compare, so I am comparing these two. I know the period and is comparing to boniko. Chloride ion siga OS ion siga. Harib and is a canana stronger nucleophile when you have to compare to boni. The HCl is a strong acid, so it forms a weak conjugate base. Due to the weak conjugate base, it is a weak nucleophile. So here water is a weak acid and it forms a stronger a stronger conjugate base. That is why it should be a stronger nucleophile. That means OS minus ion is stronger nucleophile than chloride ion. In the main toning is an example in type 1. So let me see one example here. Chloroethane is react by OS ion. We form alcohol methanol seme. So this we call it Libin group kawi. See chloride ion is a Libin group kawi. So here we are comparing these two nucleophile. OS ion is stronger nucleophile than Libin group. Chloride ion is a weaker nucleophile. That is why the stronger OS ion can replace this weak nucleophile. That is why this reaction is called nucleophilic substitution reaction. In the nucleophilic substitution reaction, a stronger nucleophile always replaces a weaker nucleophile. So another point is that a highly electronegative atom is poor nucleophile. Highly electronegative atom say poor nucleophile name. because highly electron negative atom tends to attract the electron, not donate the electron. Where the electron attract donate to be mahuta. So here, as the electronegativity increases, nucleophilicity decreases. Electronegativity hengelige by nucleophilicity handagane. So let me give one example here. So in this example, since the order of electronegativity is smaller, carbon less than, nitrogen less than, oxygen less than, fluorine. Electronegativity is sum hengala in carbon dagi fluorine daga. So the order of nucleophilicity is kamala ani sige carbine kawiko CH3 minus, NH2 minus, CH3 minus is greater than, NH2 minus is greater than, OH minus is greater than fluoride ion. Because this central carbon atom, central atom since magi electronegativity se sina quite PA, sina quite saw. In the second point, if the electronegativity increases, then nucleophilicity will increase. So this is the concept about which nucleophile is stronger and which nucleophile is weaker. I think you understand this thing. So now now we again in nucleophilic substitution reaction. Continuation tawrasiko. So here, this thing, why haloalkane undergoes nucleophilic substitution reaction. So haloalkane se nucleophilic substitution reaction thopai maram karigino haibase I know the explain tawiyam. So I have also mentioned now that nucleophile is an electron-rich species which is always attached to the electron-deficient side of substrate molecule. So here haloalkane is a substrate molecule where the nucleophile is attacked. So we know that haloalkane, so this carbon diax bond, see carbon we doing in haloalkane, the carbon diax bond is polar in nature because this halogen is more electronegative than carbon. In haloalkane, C-X bond is polar in nature due to the more electronegative of hydrogen atom than carbon. Electronegative. As a result, the carbon atom acquires partial positive charge. Electron density walagadi positive charge purani, which become a good site for the attack of electronucleophile. And then electron deficient wherever koigi nucleophile attack tobakanda yamna tobu nuaiba jaga am weraneba. Hence, nucleophilic substitution reaction takes place. That means why in haloalkane C-X bond is polar in nature due to the more electronegative of halogen than carbon. As a result, the carbon is deficient in electron which carries positive charge. So this positive charge carbon becomes the good side for the attack of nucleophile. That is why haloalkane undergoes nucleophilic substitution reaction. So here Nu minus is a better nucleophile. That living group halide ion is a weaker nucleophile. Sigi ena pidibasida sina better nucleophile warani koi living group when chatkiba C-X bond se talaga anion chatkiba se living group to nakari warani weaker nucleophile warani. So that is the reason why haloalkane undergo nucleophilic substitution reaction. Similarly, so next we'll discuss about type of nucleophilic substitution reaction. So we have two types of nucleophilic substitution reaction. The first one is SN2 reaction. The second one is SN1 reaction. SN2 reaction means substitution nucleophilic bimolecular reaction, and SN1 reaction means substitution nucleophilic unimolecular reaction. So we'll start from SN2 reaction. SN2 dagi haurasiko. So in order to understand, so I am giving 4 points that I am giving the 4 points. Step mari hai tareko. Step mari dinatre and the points in the between we paban wine behind. So point number 1 day yango. The reaction is second order kinetics. That is, the rate of reaction depends upon the concentration of both nucleophile, both haloalkane and nucleophile. Haibadi SN2 reaction se second order kinetics ni. Magi rate of reaction se, the rate of reaction depends upon the molar concentration of both haloalkane and nucleophile. That depends on. So what do you understand about the second order kinetics? So that we learned in unit number 4, chemical kinetics. So let me repeat let me tell something about it. So ahamada rate law is karino haibase hapet palamge ko in order to understand second order kinetics khangnaba ko chemical kinetics tabudi ojan tala ani understand tawnaba ko rate law haibadi kaino haiba kanta the mathematical expression which indicate the rate of reaction in terms of molar concentration of reactant haib. That means the rate, according to law of mass action matungina, the rate of reaction is directly proportional to the molar concentration of the reactant. And the reaction amagi rate say magi reactant we molar concentration here like the reaction rate to hangale hype. So here the rate law is na kaino kanda, it is the mathematical expression which indicates the rate of reaction in terms of molar concentration of the reactants, but it should be the experimental fact, whereas the law of mass action is a theoretical concept. Aduna nana karigumba reaction amagi magi rate law ige haiba taragati sita hari se reaction amagi rate law ige haiba taragati magi the rate of reaction to kanaga magi the rate of reaction to kaida phungdo e kanda in terms of molar concentration of reactant the phungdo e have the reaction lama tapana traga thuba have se magi reactant we concentration depend to have ni have so the piece ko mathematical form the phungdo podo that we call it rate law ka way. So in this example yangasi an SN2 example the silere. So this is chloromethane sodium hydroxide. So here OH minus XS nucleophile. So OH replace chloride ion sile. So methanol plus sodium chloride same. So here the rate law of the above reaction jenang sumaini inani rate equal to K molar concentration, the product of molar concentration of haloalkane and molar concentration of nucleophile square is molar concentration hybrid. And the order of reaction see concentration term the kariba power tension of do order kawi aduna see order sikayano 2 oiba sinamar moiraga this reaction is called second order kinetic side. And order hybrid the sum of the powers to which the concentration terms rise in the rate law of the reaction. We reaction the rate law we concentration term the kariba power mayam tension never do order kawe. So in a PDB example see the magi power si 1 lere 1 plus 1 2 this is second order reaction or we call it second order kinetics. So SN2 reaction is second order kinetics oire and sorapaman with the explanation tawre because the rate of reaction depends upon the concentration of both haloalkane and nucleophile. Sina be point oire. Next point it takes place in one step amadalo iganebako that is the attacking of nucleophile and the breaking of CTAS X bond of haloalkane takes place simultaneously, and the nucleophile attacks from the backside of haloalkane. So here, so this is the nucleophile I am drawing in 3 dimensions. The yekpaniko. See, 3 dimensions. The yepakanda sigi sina on the plane of paper the layer ga dot sina plane dugi maning the lagadaba sina plane sigi mamanda lakadaba my angle the magi CS4 SP3 or a tetrahedral shape we have a core. So in the second point I say the attack of nucleophile here always single step web. This is single step reaction where the attack of nucleophile is always attack from back side to attack to the back side of the substrate molecule the attack to the attack of the nucleophile to the carbon atom of C-X bond and the breaking of C-X bond takes place simultaneously. Sigi attack to the pochiga sigi tatkiba all bond tatpaga new bond semaga matamam tata tominani haibane sino new bond ama semani sino old bond se tatkarani se takes place simultaneously. That means it is a single step reaction haibane ko. And the nucleophile is always attacked from the backside of substrate molecule attack tawni have ko backside to attack tawni kari marangina kanda if it attack front side attack taw targadi sisu minus pure sisu minus pure apani marakta that is possibility electrostatic repulsion thopa yawi possibility laibagini have ko. Next point to kai hano the reaction occur through formation of unstable transition state in which both the reactants are partially bonded and being unstable it decomposes to form product. Haibati magi reaction se the reaction is occur through the formation of unstable transition state in which both the reactant and both the reactants are partially bonded. Haibati see transition state haibati kano kanda it is this state is in between the reactants and the product. Transition state haibati kano kanda it is unstable state which lying in between the reactants and the product. Koi reactants and product ki marakta laiba unstable oiba state niko and its lifespan is very short. Why this transition state is unstable? Because here how many bonded here in how many bond around the carbon atom 1 2 3 4 5 and carbon atom bi akoi da bond kale kanda si partially bonded or su bond kale 5 layer banina si unstable or so it is immediately decomposed to form product same gane ko yam thuna kai thagi ne ko duna. So here the reaction occurred through the formation of unstable transition state and the transition state is unstable. Its lifespan is very short, so it immediately decomposed to form the product same gane ko. Next point the reaction is accompanied by the inversion of configuration. I don't know reaction se top kan the inversion of configuration. Magi configuration se matanga on top haiba. Configuration matanga on top haiba nang satin se nuksi chilapa kanda satin je nuksi chilapa kanda sumaina layer poto muk sumaina on to idana ko. Atuni inversion of configuration haiba. So here stay yang si. Sida layer sigi dotted line si sumakan side layer. Sumakan left side layer. Ko left side layer mo potse mo kaida layer dotted lines ga solid lines ga right side tong lai. This is a mean to is my configuration se inversion to be high never ko. So in the substitution reaction the inversion of configuration takes place. Small layer ko. So let me repeat again. The points here. SN1, SN2 reaction to give magi magi thokipa magi point mayam to hapitang sarapa ma amu repeat tausi ko. Number 1 point is kaino haibakanda the reaction is second order kinetics. That means the rate of reaction depends upon the molar concentration of both haloalkane and the nucleophile. Next pointer, it takes place in single step. That means the attack of nucleophile and the breaking of C X bond takes place simultaneously, and nucleophile is always attacked from the backside of substrate molecule, and the reaction is proceed through the formation of unstable transition state. This transition state is unstable because this carbon atom is bonded by 4 bonds, bond to vehicle, and its lifespan is very short, so it decomposes immediately to form product. And the next one is the reaction is accompanied by the inversion of contribution. My contribution is change to si oidune sinica hangmani pekada dum magi si reaction complete this reaction haraga write the mechanism of this reaction haina adum hangi ko to marks pira. I think you understand it. Now let us see the reactivity of types of haloalkane in SN2 reaction. So I am giving the order here. The increasing order of reactivity in SN2 reaction is tertiary haloalkane less than secondary haloalkane less than primary haloalkane. The reason is that in SN2 reaction the nucleophilic attack takes place from backside on alpha carbon atom. Alpha carbon atom means the carbon atom carrying halogen atom. Halogen atom puriba carbon se alpha carbon atom kawi of haloalkane. Therefore, the presence of bulky alkyl group on or near the alpha carbon atom gives more steric hindrance. Steric hindrance means more block on the approach of nucleophile to the alpha carbon atom. Therefore, the reaction is slow. So this means that if there are less number of alkyl group around the alpha carbon atom. So in this example, we have 3 alkyl groups attached to the alpha carbon atom. Due to the presence of this bulky 3 alkyl group, it hinders or it gives steric hindrance on the attack of nucleophile, say for example OH ion to the alpha carbon atom. As a result, the attack of nucleophile is slow. That is why consequently SN2 reaction is also must be slow. So always tertiary haloalkane usually does not occur SN2 reaction. Usually it occurs SN1 reaction. Tertiary haloalkane the ayamana SN1 reaction to SN2 reaction the token they have a core due to the presence of this bulky alkyl group around alpha carbon atom, which hinders the approach of nucleophile. So in this case, this is primary haloalkane having only one methyl group at alpha carbon atom. So due to the presence of less number of alkyl group, the approach of nucleophile to the alpha carbon atom is very easy. That means this only one methyl group does not give any steric hindrance on the approach of nucleophile, say for example OH ion. That is why this reaction is faster. So usually primary haloalkane undergoes SN2 reaction. So in this way the order of reactivity of haloalkane in SN2 reaction is tertiary less than secondary less than primary haloalkane. So in other in order to understand these things, so let us discuss some questions related to this mechanism. So let us see the question number 1. Which haloalkane is more reactive in SN2 reaction? Why? I have a haloalkane and compare to out of these two haloalkane, which one is more reactive? So in the first one, I am giving 1 bromopropane and this is 2 bromopropane. 1 bromopropane is primary haloalkane, 2 bromopropane is secondary haloalkane. So let's see the answer. 1 bromopropane will react faster in SN2 reaction because it being a primary haloalkane, gives lesser steric hindrance the approach of nucleophile at alpha carbonatum than that in secondary haloalkane. So this is the reason. The primary haloalkane gives less steric hindrance on the approach of nucleophile at alpha carbonatum than that in secondary haloalkane. The next question is, this is bromomethane and another one is iodomethane. Out of this, which one will be more reactive in SN2 reaction? So you have to compare which one will be the better living group. Kanana better living group we have to yang tare. In SN2 reaction we have to break this C-Br bond and we have to break C-I bond. So after breaking this bromine, remove S-bromide ion, then is living group. Out of this bromide and iodide ion, which one will be the better living group? So here iodide is better living group than bromide ion. So here is the answer. Since iodide ion is better living group than bromide ion, because of lesser bond dissociation energy of C-I bond than C-Br bond. C-I bond tatpada sangba energy tuga C-I bond tatpada sangba energy 10 means bond dissociation energy tuga sigi C-I bond tatpada sangba bond energy tuga C-Br bond tatpada sangba energy tuga sigi C-I bond tatpada sangba energy na low oyaneba, because this bond length is longer than this bond length. Si bond length na sang neba. Sitagi ko kalimarangino kanda iodine has larger atomic size than bromine. Aduna bond yamain tatapat taragati si iodide se better living group oira neba. Sitagi compare to kanda. Aduna iodide is a better living group than bromide ion due to the lesser bond dissociation energy of C-I bond than that of C-Br bond. That is why methyl iodide will react faster than methyl bromide in SN2 reaction. Sina better living group ta compare to raga kunguda answer ni. Next question di yang asiko. Next question sidi only arrange to. Arrange the following haloalkane in increasing order of SN2 reaction. Aina sida haloalkane khara pyramid types of haloalkane primary, secondary, tertiary pyramid. However, mayam say we have to arrange in the increasing of SN2 reaction. Arrange to tare. The aham say 1 chlorobutane, 2 chloro 2 methyl butane, 2 chlorobutane, 1 chloro 2 methyl butane, 2 chloro 3 methyl butane. Si mayam si pire. And it's clear when we see to echo. So here the order of reactivity of haloalkane in SN2 reaction is SN2 reaction is tertiary less than secondary less than primary. So here, without writing the formula, how can you know this? How can you know whether the haloalkane is primary, secondary, and tertiary haloalkane? Nana formula sui the bida pyramid by hello can may have the carbon primary no, secondary no, kando piralore. Doing matungin and stop to ko. So this one is primary haloalkane because this chlorine atom is attached at the terminal. So carbon number 1 the naptargadi. Any halogen se carbon number 1 naptargadi. To carry any primary haloalkane with a name. And tareko. So this is tertiary haloalkane because the formula of tertiary haloalkane is here. So see parents and in the tertiary haloalkane, this carbon atom attaches one alkyl group, and this carbon atom attaches this functional group halogen atom at the same time one alkyl group. However, sigi alpha carbon sida alkyl group amaga halogen atom amaga plug laminaba taragadi that haloalkane is tertiary haloalkane. So here 2 chloro and 2 methyl. So this chlorine atom is attached to the carbon number 2. This alkyl group methyl is attached to the carbon number 2. So this is same as like this. So this is tertiary haloalkane. The tertiary haloalkane orani. The next one, this is 2 chloro 3 methyl butane. 2 chloro 3 methyl butane. Here, in this case, this halogen atom is at the non-terminal carbon atom. So here, the secondary haloalkane, this is secondary haloalkane. In the case of secondary haloalkane, this halogen atom attaches to the non-terminal carbon atom. Non-terminal carbon atom that attaches to the secondary oitai. So here, this will be secondary haloalkane because this chlorine atom is attached to the non-terminal carbon atom, and this is substituent methyl group. So the position of this chlorine atom and the position of methyl group is different. So this will be the secondary haloalkane. The position of haloalkane and methyl group are similar. This is tertiary haloalkane. So here the position of this chloro halogen atom siga methyl group ko khenarabanina, this is secondary haloalkane. Then this one is primary haloalkane because the chlorine atom is attached at the terminal carbon atom. In this way, without writing the formula of haloalkane, we can know which one is primary, which one is secondary, and which one is tertiary. So in this question, the increasing order of types of haloalkane in SN2 reaction is you pass right tertiary less than, secondary less than, primary. So here this is tertiary haloalkane, and higher this is tertiary haloalkane is less than, this is secondary haloalkane. These two are secondary haloalkane, but in this case one methyl group is attached here, there is no methyl group. So if the methyl group is attached, it will give more steric hindrance as compared to this thing. Similarly, and this one is, let's compare these two. So this one is primary haloalkane and methyl group is attached to this carbon number 2, and in this case there is no any methyl group. So this 2 is primary, this 2 is secondary. So this will be less reactive due to the presence of this methyl group. In this way we can arrange the increasing order of SN2 reaction. Tertiary less than, secondary less than primary. So without writing the formula of molecule, you must know which one is haloalkane, which one is primary, secondary, tertiary haloalkane. Karmano aina takibo do kando agalore. Sibo ienga siko aside.